So the first part is going to be Poincaré maps. I'll kind of go over it briefly. So first I'm going to have to give you a few definitions. So we're going to first start off with a definition of a periodic orbit. So let's write it down formally and then I'll draw each of these things. So suppose phi t of x star is a periodic orbit So suppose that is a periodic orbit of this differential equation of x dot equals f of x, which is continuously differentiable. So we're going to denote it as that. So C1 means continuously differentiable. C2 means it has two derivatives that are both continuous. So that's what that means. So this has at least one derivative that is continuous. Of period t. So we're going to denote the period of this periodic orbit as t. And then formally, in set notation, we can write it like this. So we're going to call this periodic orbit gamma, and we're going to write it as this. So all points x in Rn such that x equals phi t of x star, and with the parameter t going from 0 to big T. So that's how we write this definition in set notation. So you don't have to be too used to set notation, but if you do more math, then you'll get used to it at some point. So that's what we're going to call a periodic orbit. So basically, if we're drawing this in, say, 3D, it's going to look like this. So it's going to look something like that. And let's take, so that's a periodic orbit. And let's call this x star. So basically, we're flowing this x star around for time t equals big T, and then that will capture this entire periodic orbit. So that's what a periodic orbit is. Now, to set up the Poincare map, so the idea of a Poincare map is we're going to put some sort of section into our flow, and we're going to see what happens in that little manifold. So that's the idea. So now we're going to have to define what that manifold is, what that hyperplane is. So let sigma be the hyperplane orthogonal to gamma. So it's a hyperplane orthogonal to the periodic orbit gamma at this point x star, whatever x star may be. And in set notation, we can write it like this. So sigma is going to equal the set of x in Rn such that x minus x star dotted with f of x star equals 0. So that's how we're going to define sigma. So basically, sigma is this section that we're going to put into the flow. So we want this to be orthogonal to gamma. So we're going to put this section in, and I'm going to have to draw this a little better. But basically, we put this section in, and we're going to call this sigma. And that's going to be orthogonal to gamma at x star. So let me draw this better. So it's going to look like this. So here is, and I should label what this is. So this is the periodic orbit gamma. This is some x star at some point that we're going to use as reference. And we're going to put a hyperplane that's orthogonal to gamma at that x star. So that's basically how these things are defined. So we're putting in a hyperplane, and then we can look at the flow that happens near this x star. So that's the idea of this. So we do have one more definition that we need to fill in. Or rather, I'll give you a theorem first, and then I'll give you a definition. So this is kind of a small theorem. So this says there is an epsilon greater than 0 and a unique function tau of x that's continuously differentiable. So we're going to see this continuously differentiable a lot. For x in this ball of radius epsilon around x star. So we can only do this near x star. We don't have the machinery to do this too far away from x star. So this works only near x star. So we're going to have that, such that, st means such that, tau of x star. So let's see how this is defined. So we're saying that there's an epsilon greater than 0 and a unique function tau of x for x in a ball around x star. So some small ball around x star. Now, tau of x is going to be the function of time that some x takes to come back. So basically what tau of x means is that it's going to be the time that you're evolving x, and the next time that it hits that, that transversal, that sigma. So what do you think tau of x star would be in this case then? So basically tau of x star is going to be x star, but then the time it takes x star to come back and hit sigma again. So what do we think that is?
Period.
Okay, what is that? What did we say that was?
Sorry I'm late. I have a note for my profession.
So we have the right here, right?
Yeah.
So it's going to be t. So tau of x star is going to be t. And we have that phi tau, so phi sub tau of x is in sigma. So that's basically what we said before. So tau of x is going to be the time that it takes for some point to come back to, so the flow of some point to come back to sigma, to our transversal. So this is saying that the flow for time tau of x of some point x is going to come back to sigma. So that's basically what we said in words. And this is for all x in B epsilon of x star. So the ball of radius epsilon around x star. So some small neighborhood around x star, basically. So we can draw that like this. So this is some ball of radius epsilon around x star. So when we think of these sort of theorems and definitions, we're thinking of it inside this particular ball. Except I should write this like this. So I'm drawing it on sigma, so this is actually the ball around x star that's intersecting sigma. So I should write it like this. So this is the ball around x star that's intersecting our hyperplane. So that's that. And then now we can define what the Poincaré map is. And then I'll draw some of the iterates in the Poincaré map. So we're going to define our Poincaré map as such. So we're going to use this phi tau of x of x. So we're saying for x in this ball that's intersecting sigma, the function p of x, which is going to equal phi tau of x. So this function is called the Poincaré map. So that's called the Poincaré map for gamma. So for the periodic orbit at x star. So that's how we define the Poincaré map.
Also known as the first return map for obvious reasons. First time it comes back, it intersects the transversal the first time.
Right. So we can either call it the Poincaré map or the first return map. So that's the idea of the Poincaré map. Now we can look at some sample iterate. So let's take, say, x naught over here. So let's take this as x naught, and we're going to flow this around. So this is going to be coming back like this. And we can call that x1. So this is x naught, and this is x1. So here, x1 is going to equal p of x naught. And it's basically just taking this, flowing it until it hits our sigma. So that's the idea. So it's a very simple concept. We're going to take this x naught somewhere in this ball, and we're going to flow it around and see when it hits sigma. So that's basically the idea for a Poincaré map. So any questions about that so far? Yep.
What's the purpose of this map?
That's a good question. So, dealing with the stability of periodic orbits is difficult, right? So, we don't quite know how to deal with it. There isn't a very easy way to deal with that sometimes. But if we use a Poincaré map, so let's say for here, we're just taking this this hyperplane, and we're going to intersect this periodic orbit. Now we can very easily figure out what the stability is of this, so we can do some analysis on, for the periodic orbit using this map. So we're doing the analysis on the map, but it's for the periodic orbit. So we can learn some things about the periodic orbit just by looking at this map.
Okay.
So this Poincare map will have, of course, the same properties as maps we've learned before, maps we've dealt with before.
Okay. Okay, thank you.
So we'll see this in an example that I have. So it's actually very difficult to come up with an example for Poincare maps. So this example I took from Perco. So this is quite a good example. But in general, it's difficult to find the Poincare map explicitly. But it's important because it gives us theorems that we can use. So we can deal with it theoretically. But let's look at this example. And I'll give you guys the homework as we go along on this example. So this is x dot equals negative y plus x times 1 minus x squared minus y squared. And y dot equals x plus y times 1 minus x squared minus y squared. So it's going to be that. So you can see it's a very carefully constructed example. So I don't know if Perco was the one who kind of came up with this, but whoever came up with it obviously took a lot of time to carefully construct an example that could be used for Poincare maps.
Maybe Poincaré came up with it.
Yeah, maybe, who knows? Yeah, I have no idea who actually did come up with this. So this is the first homework assignment that I want you to do, and I'll email you guys this too, but write it down just in case. So I want you to get used to solving differential equations using ODE 4.5. So solve this using ODE 4.5. And then, so when you do solve it, plot x and y. So let's see, do I want you to plot x versus y? Yeah, plot x versus y. Or y versus x, whatever it's called, whatever the convention is. So solve this and then give me the phase plane, basically. But not through p-plane. Of course, you can use p-plane to help you out. Okay, so that's the first step. But we have this, but it's kind of difficult to see where a periodic orbit here would be. So any ideas? Do we see anything that we can use? Do we see anything that we can do to this to make it easy to find the periodic orbit? So there's some things here that should kind of give you a hint. So let me write it like this. Let me write this as this. How about now? Do you see a transformation we can use? Something that we might have done in Calc 3.
Polar coordinates?
Yeah, so we can change this to polar coordinates, right? So this is the second part of the homework. So let me just write it down. So when we change it to polar coordinates, it's going to be r dot equals r times 1 minus r squared, and theta dot equals 1. So the second problem in the homework is going to be to do the transformation explicitly. So write out the steps for the transformation. But before we do that, just so I know you guys know how to do polar coordinates, how are we going to start the transformation?
Let x equal r cosine theta,
Okay.
and y is equal to r sine theta.
Okay. So you're going to use this, right? So you're going to let x equal r cosine theta, y equals r sine theta. Obviously, x squared plus y squared is r. And you're going to take this, plug it in, and then come up with the system in polar coordinates. So do the steps for this transformation. So we have this. Now do we see where the periodic orbit is? So theta dot equals 1, right? What does that mean?
The change in angle is constant.
Right. Exactly. So it's not changing depending on theta or r, right? It's just changing depending on t. So that we don't have to worry about. But how about that? So can we figure out what the periodic orbit is from here?
It's an easy
Um,
one.
It's gonna be similar to the equation that we did last class.
I forget what we did last class, but it might be, yeah. I think we did something like that.
Logistic equation?
So the logistic map. Okay, we might have something similar, but so what happens at r equals 0?
Change to 0?
Yeah.
So it's a fixed point, right? It's just 0. Do we see any other fixed points?
1.
Okay.
1, -1.
So we have 1, but okay, so -1 as well, but it's a radius, right? It's r. So we could just consider it as r equals 1. What happens at r equals 1?
Fixed point.
It's a fixed point, huh?
The change is 0.
Okay, so it's a fixed point, so r is always going to be 1, right? So it's just going to be coming around. So it's a circle, right? At r equals 1. So here the periodic orbit is going to be r equals 1 as theta goes around. But now we can write this in terms of x and y. Or not in terms of x and y really, but we can write the periodic orbit for x and y. So for this, in this system, how would we write it?
What are we writing in terms of x and y?
So we want to write r equals 1 in this system.
Oh.
But of course, as theta is changing, right? So theta is changing as t.
Mm.
So theta equals t plus some constant, right?
Mm.
So this is the periodic orbit. So when r equals 1, we get the periodic orbit. But now we want to write it in terms of x and y. So how do we do that?
X squared plus y squared equals 1.
Okay, but let's write it like this. X, y, what does it mean for that vector? What is that vector going to have to be? So r equals 1.
So it's going to be a cosine theta and sine theta?
Okay, but then theta is just t, right?
Mm.
Theta dot equals 1. So we can write it like this. Cosine t and sine t. So that's our periodic orbit. Up to a constant, of course. So we can write it like that. So now we have our periodic orbit. So let me see if I give you the current homework now or later. Okay, so I'll do that later. But we can solve this. So we notice that we can solve this. I'm not going to make you guys solve it because you've done enough of that in ODE. But we can solve it to get this. So if we solve these two equations, we get this. And then we're going to derive our Poincare map. So r is going to equal the square root of 1 plus...
How would you solve that first equation?
Yeah, how would you solve it?
Jacobian?
No. So, okay, how would you solve this second equation?
That's easy.
That's easy, right?
That's integrate.
So here you just integrate it, but then how about this one?
A separation of variables?
Yeah, exactly. So you can use separation for this.
Partial fractions.
But the first one, don't you have to use, no, I'm talking about the one up.
Yeah.
That one. Yeah, don't you have to use the Jacobian just to solve that one?
Oh, so you mean to analyze it? Analyze the phase
Yeah.
plane?
Yeah.
Yeah, so you would have to compute the Jacobian, find your fixed points, and then do the stability analysis and all that for this. But here, you can very easily solve this equation analytically.
Okay.
But I won't make you guys do that. So this is going to be 1 plus 1 over r of 0 squared minus 1 times e to the negative 2t. And the theta equation is going to be theta equals t plus theta of 0. So we're going to get that if we solve it. So since this is in 2D, we can kind of sketch it as such. So let me use blue for the orbits. So use black for this. So let me write it like this, and then this is x and y. So now we want to see what we want to do with this information. So we have this, and we want to kind of construct the Poincare map. So we know that we're going to get a periodic orbit at r equals 1. So we can go ahead and draw that. So let's draw our periodic orbit at r equals 1. So this is very poorly drawn, but here, let me try to draw it better. Or let me try it like this. So I'm going to draw the periodic orbit first, and then sketch the coordinates. All right, so that's a little better. So that's the periodic orbit. And let's just say what theta of 0 and r of 0 are. So let r of 0 equal r naught, and theta of 0, running that as theta of theta. Theta of 0 equals theta naught. So now, if we want to choose a transversal, if we want to choose our sigma, how do we want to choose that? So first of all, what is the geometry of our hyperplane going to be in this case?
Perpendicular to the circle.
Okay, but what sort of object is it going to be? What's
Line.
What's half a line?
What's half of a line?
Yeah, like not half a line, but you know, a line in only one direction, like that crappy band.
Vector.
Array, right?
Oh what?
Array.
Ray.
Oh, yeah.
Yeah. So we can draw array. So how do we want to draw this ray though?
At, I guess R0 and theta 0?
So not at r naught. So r naught is just whatever it is at.
Yeah, theta.
Exactly, at theta naught, right?
Mhm.
So we want to draw this ray at an angle theta naught that intersects the origin, right? So let's draw it like this. Let's say theta naught is here. So we want to draw this ray like this. And this is theta naught. So that's how we want to draw our sigma. And let me just label these things. So this is gamma. And this is sigma. So that's how we want to draw that. So we have that. So now let's try to figure out what our, so let me just ask you this first before we figure it out. What's our x star going to be in this case? where is our x star going to be?
It's going to be where circle intersect the right.
So it's right there, right? So that's our x star. So now that we have that, what do we think the period is going to be for that? What is the period for this periodic orbit? So theta dot equals 1, right? So theta dot is, so theta is moving as t, and we're going around in a circle, so then the period is?
2 pi.
So it's 2 pi. So here our period is t equals 2 pi. So we have that, we have x star, and now we want to figure out what our Poincaré map should be. So let me see, okay, so we have everything we need. Now we're going to figure out what the Poincaré map is, and then I'll give you guys your final part of the homework. So how are we going to figure out, how are we going to take this information and figure out what the Poincaré map is? So this is what we want to do, right? We want to have a map that goes from here and comes back around and intersects sigma again, right? So we want to take a map that starts at sigma, goes around, and hits sigma again. But how are we going to do that?
You could, I guess, iterate it or plug it in. But don't we gotta have like a ball or something like that just to have?
Yeah, sure. So we're just around some small area around x star.
Okay.
Right? So let's think of a small area around x star, and we want to take a point and then flow it around, and we want to intersect sigma again.
Okay.
So what's that map going to be? So let's take a point here. So let's pretend this is a fairly, it's a small ball, but we're magnified. So let's take some x naught here, right? And we want to flow this around, right? So we're going to flow this around, but we're going to flow it around for 2 pi. So it's going to hit, say, here. So that's x1. So now x1 equals p of x naught. So it's going to be something like that. So we want to take this x naught, we want to flow it around for 2 pi, and then we're going to hit sigma again. So now if we flow it around for 2 pi, what's changing?
R.
So r is changing, right? So theta is not changing, but r is going to change. So do we have an equation for r?
Yes.
So we have it right here, right? So we have an equation for r. Now we have r naught here, right? So we have some r naught squared, and then we have a t. What do we do with this t though?
Change it to 2 pi n.
So 2 pi, right? So it's a first return map, so we only want the first, like we want the smallest period, basically. So we don't want it to come around twice until we iterate again. So yeah, this is going to be 2 pi. So here, t is going to be 2 pi, and that's the Poincaré map. So p of Rn is going to equal the square root of 1 plus 1 over Rn squared minus 1 e to the 4 pi. So that's our Poincaré map. So we only want to evolve this around for 2 pi. So if we want to do that, the only thing that's changing is the radius. Well, how do we find out how the radius is changing? We have an equation for that since we solved it. So since we solved it, we have an equation for how the radius is changing, and that is just going to give us our Poincaré map. So that's our Poincaré map. And now we can do some analysis with that. So now that we have a map, we can do some analysis, and this is going to be Rn plus 1. So what do we want to do first, now that we have a map?
Did we change it to a discrete system now?
Yep.
Okay.
So now it's a totally discrete system. I mean, this map is totally discrete. So this is a discrete system. So what do we want to do first? What do we usually do with any dynamical system?
On the fixed point.
Okay, so we know what the fixed point is, right? So let's just write down what the fixed point is since we already found it. So what is that?
0 and 1.
Or
Oh.
It's what?
or is equal to 1.
No.
Oh.
Well, okay, yes. Sorry, yes. So I was thinking just x star, but yes, it is r equals 1. Yeah. So here, our fixed point is going to be r star equals 1. So the fixed point for this map is r star equals 1. So that's our fixed point. And now what do we want to do?
Determine stability.
Okay, so how do we do that?
Take a derivative.
All right. So let's take a derivative, and I obviously didn't do this by hand. So this is p prime of Rn, which is going to equal e to the negative 4 pi Rn to the negative 3 times 1 plus 1 over Rn squared minus 1 e to the negative 4 pi to the negative 3 over 2. So we have that as our derivative. So then what's the stability going to be? Or how do we find the stability?
So change is less than 1, the absolute value.
Okay, at where?
We
At
plug
what
in,
point?
we plug
At
in
fixed
r
point.
is 1.
Okay, so we're going to plug in r equals 1. So we're going to have p prime of 1. And what's that going to equal? So if we plug in r equals 1 there.
E to the negative 4 pi.
So e to the negative 4 pi. And is that greater than 1 or less than 1?
Greater.
So that's going to be less
Or
than
less
1,
than.
right? So it's less than 1. So then that means that this periodic orbit is stable. So we couldn't find the stability of the periodic orbit very easily from this system. But now if we use a Poincare map, we can find the stability of that periodic orbit fairly easily, just through fixed point analysis. So that's the idea of using a Poincare map. That's the reason why we want to use this. So for homework, I want you to plot the time series of P for r less than 1, r equals 1, and r greater than 1 for 20 iterations. And preferably on the same plot, so you can do that using the hold on option. So you can search what that means. But if you can't, then it doesn't have to be on the same plot. So I'll email you guys this as well.
Well, you said r equals 1, r less than 1, r greater.
Yep.
Okay.
So basically for r in this region, r equals 1, so the periodic orbit, and then r less than 1. And it would be nice to see it in the same plot. So if you do it on the same plot, then you can see how things are kind of working together. But it doesn't have to be on the same plot if you can't do that. So yeah, do that. So that's all I wanted to say about Poincare maps.
Just a point. Can anybody look at the polar equations and tell from those about the stability of the periodic orbit? Take a close look at those equations and tell me why, just from the way they're set up, you know that r equal 1 is a stable periodic orbit. Look at the sign of r dot. When r dot is equal to 0 when r equal 1. What about when r is bigger than 1?
Becomes negative.
Negative.
What about when it's smaller? It's positive. So inside the circle, R is increasing with time, outside it's decreasing, so it's winding into that periodic orbit.
So yeah, this example was kind of doctored to be simple to find the Poincare map. So obviously we could have used some other analysis to find out what we wanted for this as well. So that's all I wanted to mention about Poincare maps. So any questions before we move on to structural stability? Or anything you would like to add?
No, not so much at this point, except just to think about what Poincare maps do. They sort of have a reduction property, and they also tell you a lot about the dynamics just by looking at these maps. For example, you're going from a differential equation in n-dimensional space to a map of n-1 dimensional space, okay? So you change from continuous n-dimensional to discrete n-1 dimensional. And if you look at other properties, the properties of the Poincare map, of course, are good for determining periodic orbits. Fixed points of the Poincare map, of course, do correspond. But you can also see other things. For example, if the Poincare map is chaotic, behaves very strangely, then you know the orbits are going to behave very strangely as well. So it's sort of a reduction where if you can analyze that, you can say quite a bit about the original system that you come from. It also turns out that it works the other way. There's a procedure whereby if you know what the Poincare map is, I can set up the continuous dynamical system that gives you that Poincare map. So in a way they're equivalent, not easily so.
Right.
But very often people will discover things about these systems by looking at Poincare maps. They're very useful tools.
So I kind of wanted you guys to just get a feel for what Poincare maps are and what they are used for. So now we're going to do some structural stability. And this might be kind of a difficult section to go over because there's a lot of topology and a lot of really pure math stuff that you guys might not have seen since we're an applied math department. But I'll try to kind of break it down as much as possible for you guys. So this is lecture 5B. Structural stability. So what we're going to do for this is define a bunch of stuff. I'll obviously define structural stability, and then we're going to prove a special case of Peixoto's theorem, which is the main structural stability theorem. And then hopefully you can get a feel for what structural stability is. So hopefully we can do this in an hour. So let me just define what hyperbolic and non-hyperbolic fixed points are first. So a fixed point x star is said to be hyperbolic if f prime of x star does not equal 0. Otherwise, it is said to be non-hyperbolic. So this is probably something most of you have seen. So you probably...
This is one-dimensional, right? So this is a mapping from the line.
Right.
And this from the,
So I'll set up the one-dimensional problem after I kind of give you these definitions. But you probably have an idea of what it means for a fixed point to be hyperbolic or non-hyperbolic. So then, let's define something that you may not have seen before. So this is for homeomorphisms. So a map H going from M1 to M2, where M is a manifold, is set to be a homeomorphism if it is a bijective. So bijective means one-to-one and onto. And bicontinuous, so it's continuous and it has a continuous inverse map. So that's what a homeomorphism is. So when Ian was taking Calc 2 with me, he asked what was the class that would have the craziest sounding names. So I told him.
Yeah, I think I found it.
Yeah, exactly. So yeah, here we go. So homeomorphism, non-hyperbolic. So now you can tell your friends about all these crazy names. Okay, so let's do an example of a homeomorphism. So consider this. And let's try to prove that this is a homeomorphism. So H going from the positive reals to the interval 0, 1, defined by H equals 1 over 1 plus x squared. So let's try to prove that this is a homeomorphism. So what's the first thing we would like to prove? Someone pick something. What's a word you've seen before that you can kind of prove?
Hamiltonian.
Huh?
Hamiltonian.
Wait, what?
Hamiltonian.
No. So okay, so let's see what the definition is. A map H, right? So we have this H, is a homeomorphism if it's bijective, so that means one-to-one and onto, and bicontinuous, so it's continuous and it has a continuous inverse. So choose something that you want to prove that you could have proved in, say, Calc 1.
Continuity.
All right, so let's prove continuity. Let's prove that that's continuous. So how do we do that? And without epsilons and deltas. So I know you guys haven't had analysis, so I won't force you to do epsilons and deltas. So let's prove continuity in using the machinery we had in Calc 1. So how do we do that? So let's first show that, what is continuity? Let's write that on the side.
There are no holes in the.
Okay,
Function
so
is defined everywhere.
okay, so the limit as x approaches c of f of x is going to equal f of c, but also f of x at x equals c has to equal f of c, right? So it's not enough that the limit approaches. Of course, the limit's going to have to approach, but it also has to exist for that particular c as well, for any c. Then it's continuous over that region. So let's do that. Let's pick any c. So this has to work for any c. And let's first show that it actually exists. So h of x equals c is going to equal 1 over 1 plus c squared. So this is for any c in 0 to infinity, right? But we see that for any of those c, we do remain in this set. And it exists for all points in this set. So it clearly exists. And now let's show that the limit also exists. So for the limit as x goes to c of h of x, but that's just going to be 1 over 1 plus c squared. Right? So we can see here that we don't have to do anything funny. If we take the limit, it's just going to be 1 over 1 plus c squared. So the limit exists, so then it's continuous. So this says that h is continuous.
On the other hand, I'm teaching Calc 1, so I'm an expert. What you could do is, if you don't want to go back that far, is to recognize that once you define continuity, you start looking at classes of functions that are continuous. Constants are continuous, obviously, and it's easy to show by induction that polynomials are continuous. Then you get the rules. A ratio of continuous functions is continuous, except at points where the denominator vanishes. So this is a ratio of a constant. It's a rational function, right? And notice that the denominator never vanishes, so you can rely on some stuff you proved after using the definition.
So I actually thought of kind of introducing epsilons and deltas to them, but I figured, nah, that's probably better for analysis. Okay, so we proved that h is continuous. How about, so what do we want to do next?
Show it as 1-to-1.
Okay, let's show that it's 1-to-1. So what do we mean by 1-to-1?
That for each value x is one value y,
Okay. So let's write down what we mean by 1-to-1.
or h.
So it's going to be this. So I kind of forget what surjective and injective is, but let me see. Injective is onto.
No.
Injective is 1-to-1. Surjective is onto. Okay. Okay. So let's show 1-to-1. So this is continuity. This is going to be 1-to-1. So how do we show that?
I guess that you could show it by graphing it, or show that it's like.
We could graph it, but how do we show it analytically? So let's think of what 1-to-1 means. 1-to-1 is going to be that we have some set, and every point on this set will be mapped to some point on that set, right?
Mhm.
So what do we mean by that analytically? So let's think of this. So can we think of, okay, so we want to say that we have some set and it's going to map to that set. So we want to say that, say if h of A equals h of B, then A is going to equal B, right? So that's what that means, right?
Okay.
So if we're mapping from this set to that set, and we get some point here where so we choose some point, and let's call it h of A, and we choose another point, let's call it h of B. If they're equal, we must have that A equals B, right? So that's how we're going to prove 1-to-1. So we want to show that here. So we want to show h of A equals h of B. Or if h of A equals h of B, A equals B. So h of A equals h of B implies A equals B. So you want to show this. So let's go ahead and do that. So h of A is going to be 1 over 1 plus A squared. And that equals h of B, 1 over 1 plus B squared. But that means that 1 plus B squared equals 1 plus A squared. Well, we can cancel out the 1's. And then we get that B equals A since we're always positive. So we're not going to have a negative value for this. So B will always equal A, since we're always going to be positive. So that shows that it's 1 to 1. Now what do we want to show? So since we showed it's 1 to 1, the next logical step would be showing it's onto. So what do we want to show for onto?
What exactly do you mean by onto?
So onto basically means that if we're going from this set to this set, then that map will map points from this set to every point on this set. So 1 to 1 is basically every point on this set is being mapped to some points on this set. And an onto means that that some points on this set map to every point on this set.
Okay.
And then 1 to 1 and onto means that every point on this set maps to every point on this set. So that's the idea. So how do we want to show onto then?
To have them equal and then plug in a value just to see if you could prove that it's not by contradiction, right? Because if it goes all the way to infinity, then and then the other one is like a closed interval from 0 to 1, and then it's not going to be 1, 2, right?
Well, we don't have to use contradiction here. So let's think of how we showed 1 to 1. We basically said that there's going to be, if we have some points equal on this set, then they have to be equal on the set that we're coming from, right?
Mm-hmm.
So that shows that every single point is going to map to something here, to something on this set. But now we want to show that points on this set map to every single point on this set. So how about we do this? For all C on this set, or for all Y, let's say. So for all Y on this set, we can find a point on this set, right? So that would show that it maps to every point on this set. So this map, we don't know how many points are coming from here, but it's going to be mapped to every point on this set, right? So let's show this. So we want to show for all Y in that set, in 0, 1, there exists an X in 0 to infinity such that h of x equals 1, right? So that would give us that it's onto. So that's what we want to show. So let's go ahead and do that. So let's take y equals h of x, but if y equals h of x, then what does x equal? So we're going to take for all y in 0, 1, right? So let's just take some y. Let's just take a random y, and then let's see what x equals, since h of x equals y. So x equals what in this case? So we're going to have to go here, right? So 1 over 1 plus x squared equals y. So then it's going to be that 1 plus x squared equals 1 over y. And then we're going to get, so we're going to have this. 1 over 1 plus x squared equals y. So that means that 1 plus x squared equals 1 over y. So that means x squared is going to equal 1 over y minus 1. So x is going to equal radical 1 over y minus 1. So we get that. So let's just make sure everything's correct here. This goes here, this goes down, this goes there, and then we take the square root. Yeah. So we have this as our x. But now let's see what set this is in. So we have to satisfy this for all y. For all y, we must be in this set, right? For all y, x must be in this set. But notice that if we're going from 0 to 1, y is 0 to 1, it's going to go from 0 to infinity, right? So at 1, it's going to 0. So as we're going to 1, and as we're going to 0 here, this is getting bigger and bigger, so it's going to infinity. So this is in our original set. So that shows that it's on 2. So those of you that will take analysis will have to do plenty of this in analysis. So we showed all of that. Now there's only one other thing that we have to show, but we kind of showed it already. So what else do we have to show? Actually, we didn't show it, but
The
we'll leave it up to the reader.
continuity of the inverse function.
Okay, so we want to show that it has an inverse. Well, we kind of showed it with this, that it has an inverse,
Yeah.
right? So it has an inverse. We took the inverse and we showed that it exists on this set, right? So formally we can show it, obviously, but let's not. And then we want to show continuity, but since you showed continuity here, I'm confident that you can show continuity for the inverse, so let's just pretend we showed continuity. So we've showed everything, basically. So we showed that it's a homeomorphism, right? So that's how you go about showing that something's a homeomorphism. So now you can tell your friends that you know how to show that something's a homeomorphism.
It works great at parties.
Well, I mean, that's how Professor Blackmore landed his wife, right? All right, so that's a homeomorphism. Now we're going to the big definitions. So let me define topological equivalence. So two dynamical systems x dot equals f of x and y dot equals g of y on M are topologically equivalent so they're topologically equivalent if there is a homeomorphism H of M such that H maps oriented, and by oriented I mean that it's by increasing time, maps oriented orbits of the first system onto oriented orbits of the second. Or let me just shorten it, onto that of the second. And such an H is called a topological equivalence. So it's called a topological equivalence between the systems. So that's a fairly lengthy definition, but we'll see that it's not too complicated. So let's do an example for this as well. So let's take this as an example. Let's say that theta dot equals sine theta, and phi dot equals, not sine, of course. So if I use sine phi, of course it's going to be topologically equivalent, but it's going to be topologically equivalent trivially, right? Because it's the same system. So cosine phi. Let's use that. And we want to show that it's topologically equivalent. So they're topologically equivalent to each other. So now we want to find a homeomorphism between the two. So let me just tell you what sets these are on. So theta and phi are on 0 to 2 pi. Or sorry, I should say actually, not 0 to 2 pi, but on S1. I'll tell you what S1 is. So theta and phi are on this circle. So I don't want to say 0 to 2 pi because I want theta and phi to be able to go around as many times as I want. So it's on this circle. So we're thinking of differential equations on this circle. So theta and phi are on this circle, right? And we have that theta dot equals sine theta and phi dot equals cosine phi. So is there a way we can match up the two?
You could add a pi over 2 to sine.
Okay. So we could do either one. So you want to do it to sine?
Sure.
So theta equals phi plus pi over 2, right? So that would match them up. So now we're going to do this. So if we want that, so yeah, so that would match them up. So then how do we want to define our homeomorphism? So H is going to go from what set to what set? So here H is just going from S1 to S1, right? Since both theta and phi are in S1. So it's just going from S1 to S1. So it's just going to go map this circle back to the circle. But now we want to define it, defined as, in such a way where the orbits of one map to the orbits of the other. So let's define it as this. So H of phi, so since we chose theta to equal a function of phi, we're going to say H of phi equals phi plus pi over 2. So that's our homeomorphism. So now if we do this mapping, so this just basically means that theta is going to equal H of phi, right? So if we do this mapping, then we can map the orbits of one, an oriented orbit, so in forwards in increasing time, to the orbits of the other. So that's why they're topologically equivalent. So we kind of know that they're topologically equivalent intuitively, but we can also show it just by coming up with a homeomorphism. So that's topological equivalence. So that's going to be very important for structural stability. So any questions about topological equivalence?
Okay, so homomorphism means that.
So homomorphisms are something different, actually. It's a homeomorphism. But yeah, go ahead.
Okay, so homeomorphism means that you change basically the values in which they are defined.
So it's just a map. So a map does that, right? So any function will do that, right? So any function will take values from one set and then give you values in another set, let's say, right? So it could be the same values, it could be different values, but that's what functions do. Now what a homeomorphism does is, so it's a very special type of function where it's going to take values of one set, completely map them to values on another set in a continuous fashion. So continuity is important. So it's going to do this continuously. And then if we want to go back, we can also go back continuously. So that's what a homeomorphism means, right? So now, I mean, if we wanted, we can find H inverse. What do you think H inverse would do? So here, H maps is going to map points in this dynamical system, in the orbits of this dynamical system, to this dynamical system. How about H inverse though?
Would map the cosine went to the sine one, or the sine went to the cosine?
So it would map
To that one.
from here to here, right?
Yeah.
So that's the idea of the homeomorphism. We want to be able to go backwards and forwards. So that's why it didn't matter if you did theta equals phi plus pi over 2, or if you did phi equals theta minus pi over 2, right? So that's what the homeomorphism gives us. So that's the idea. Any questions about that before we go on to our big definition?
Just sort of a question and an answer combined. To be topologically equivalent means is that the dynamics, the orbit structure looks the same. It's maybe deformed in some sort of a deformed way, but looks the same. And you can see it from just plotting the dynamics of these two systems. Like the first one, theta dot equals sine theta, has fixed points at 0, which is the same as 2 pi in this setup, and pi. Okay, what about the second one? It has fixed points at pi over 2 and 3 pi over 2. So it's just the same look with the same arrow structure, the same number of fixed points. It's just that you're rotating the picture a little bit. So from that standpoint, they're the same basic dynamics.
Right.
Can the radius be different? Like, and you could still map one to other if they have different radiuses?
Okay, so let me ask you this. Let's take this and let's take this. Okay? Do you think there's a homeomorphism between this and this?
Yeah.
So there is, right? So any closed simply connected curve in any closed simply connected curve will be homeomorphic to the circle.
Okay.
So the radius doesn't matter,
Okay.
right?
Yeah.
Because we can take anything. We can take something crazy like this, and that's still homomorphic to the circle.
Okay.
So that's why we want to concentrate on the circle, because the circle gives us a lot of different sets that we can work with. So we can take any closed simply connected curve. So yeah, that was a good question. So let me erase this and then
Does
I'll put
anybody know the
definition.
name of the theorem that says that these you're saying? Anybody take complex variables?
Yeah.
There's a certain kind of curve that's important in all these integrals. It's got some French guy's name in front of it.
Was also a famous basketball player.
True. In his second or third reincarnation.
Wait, what?
I said, I didn't threw me off.
No, I mean he wasn't, but his namesake was. Jordan, yeah.
He had a Jordan curve here.
So Jordan curves are closed, simply connected curves.
Which, by the way, he did prove correctly. There's a cap in his proof.
But if you're famous enough, it doesn't
He was
matter.
right.
Okay, so here's our big definition. Actually, you know what? I'm going to put this in red. So this is the definition about structural stability. So the dynamical system x dot equals f of x with, so I'll define some of these things later. I just wanted to give you the definition of structural stability first before we go backwards. So with f being continuously differentiable on S1 is said to be C1 structurally stable so it's C1 structurally stable if for every, so I'll define what it means to be, so I'll define the next thing here. So if for every epsilon greater than 0, sufficiently small, all, so this is going to mean all nearby dynamical systems. So all G in a ball of radius epsilon of F, so B epsilon 1, that's how we're going to call this, I'll define what that is, are topologically equivalent to F. So that's for structural stability. So that basically means that if we have, this dynamical system, x dot equals f of x, and if we have dynamical systems that are close enough, so if a different function, say g, is close enough to f in some way, and we'll say what close enough means, but if it's close enough to f, then that dynamical system will act the same as our original dynamical system. So structurally stable would be if we can find dynamical systems, all dynamical systems in that region, so all these g's in that's close enough to f, for all of those dynamical systems, all of them will act the same as our original dynamical system. So that's the idea about structural stability. So if we change it a little bit, we're not going to change the dynamics, right? So we're not going to affect the dynamics by changing it just a little bit. Of course, we can change it a lot, and then we can affect the dynamics. But just by changing it slightly, we're not going to affect the dynamics. So that's the idea for structural stability. Now I'll say what close enough means. So let me put this here. So we know what topological equivalence means. Write this in blue. So this is going to take a step back and say what some of these things mean. So denote the class of C1 maps of the circle. So instead of saying of the circle, let's just say of S1, since you know what S1 is, of S1 by C1 of S1, then, and this is how we're going to write our norm. So then, this norm of F, but we're going to write it like that. So it's like any other norm, but we're going to denote it as 1. So this norm is defined as the sup. So sup, for those of you who haven't taken analysis, just means the supremum of the set. So if you have a set, say 0 to 1, then the sup would be 1. So if you have this interval. Now the sup for the open interval and closed interval are going to be the same. So it's a supremum, right? Now for the closed interval, the maximum, 1, is also the supremum 1. But for the open interval, it doesn't have a maximum, but it does have a supremum at 1. So that's what sup means. So sup of the absolute value of f of x such that x is in S1 plus the sup of the absolute value of f prime of x such that x is in S1. So basically we want to control the function and its derivative. So we want to have control over both since we're saying these are C1 functions. So we want to be able to control both of them. So this defines a norm. This defines a norm on C1 S1 called the C1 norm. So that's going to define that norm. And then we say further that this norm generates a topology called the C1 topology. So we won't go into what it means for something to be a topology, but basically we can think of it as just a collection of sets. So a type of collection of sets. So different topologies will collect sets in a different manner. So that's basically what it means. So called the C1 topology in the usual way. So whatever it means to be the usual way, via open epsilon balls. And this is the one that's important. B epsilon 1 of f is defined as all g in C1 of S1 such that the norm between g and f, so the norm of the difference between g and f, is going to be less than epsilon. So that's how we're going to define this. So basically what this means is that all of g, such that the absolute value, so the supremum of the absolute value of the difference between g and f, plus the supremum of the absolute value of the difference between the derivatives of g and f, that will be less than epsilon. So that's how this is going to be defined. So all these functions, so this basically means that all of these functions, these g's, are going to be close in proximity, but they're also close in derivative. So their derivatives are also close. So that's what these mean. So instead of writing down what the full Peixoto's theorem is, let me just tell you, and then we'll go to the one-dimensional Peixoto's theorem. So Peixoto's theorem says let x dot equal f of x be a C1 dynamical system on a smooth closed surface M, then the dynamical system is C1 structurally stable if and only if it satisfies the following properties. And the properties are that all recurrent behavior, so like periodic orbits and such things like that, is confined to finitely many fixed points and periodic orbits, all of which are hyperbolic. There are no separatrices, so the second property is there are no separatrices, so that means basically homoclinic or heteroclinic orbits. So there won't be any of that stuff. So there are no orbits that connect saddle points. And moreover, if M is orientable, then the set of structurally stable systems is C1 open and dense in the collection of all dynamical systems on the surface. So that's fairly difficult to prove. So Peixoto used quite a few pages to prove this, and it's fairly involved, and it uses machinery that are too advanced for us. But we can prove the one-dimensional case. So before we do that, let me just set it up, and then we'll start proving the one-dimensional case. So let me set it up here.
While you're doing that, why would you think that structural stability would even be important in applications? It's a fairly abstract-looking thing. Why would that be something that applications people would be interested in? Well, let me sort of set it up for you a little bit. So usually what applied people do is they develop mathematical models, often dynamical systems models of physical phenomena. And then they study the solutions of these things. Typically it would be with a computer. So there would be a certain amount of error, tiny errors in everything that they do. A certain amount of error in the initial conditions. You can't do it perfectly. Suppose it wasn't structurally stable. Well, if that model they had wasn't structurally stable, some small error in computing the initial condition could give you dramatically different dynamics than the system ought to have. So it's like a robustness of the dynamics. Structural stability is a robustness which you'd like your dynamical models to have, so that you can be a little off in your measurements and some of the elements and still get the right dynamics.
So yeah, structural stability is quite important, and there's definitely, Peixoto's structural stability theorem is definitely one of the most important theorems in dynamical systems. So let's set up the one-dimensional problem. So we want to think of dynamical systems on S1, but now we want to transfer them over to a set that we can deal with better. So we talked about this a couple of lectures ago. So we want to take the circle and transfer it into the unit interval. But how do we do this? So what did we do before?
You have the length from 0 to 1b 2 pi.
Okay, but what do we do with the endpoints there?
You have 0 equal 1.
Okay, so we're identifying 0 and 1, right? So this is how we want to set up our dynamical system. So we want to say that x dot equals f of x, but now we want to say that f of 0 equals f of 1. So we can identify it, but now we have to identify, so we have to say that the derivatives are the same as well, right? So f prime of 0 equals f prime of 1. So that's what we require for our dynamical system. So we're taking the dynamical system from the circle, and then we're transferring it over to a dynamical system on the unit interval. And that's going to be easier for us to deal with. So that's how we want to set this up. So let me call this 1. So let's call this entire thing 1. This dynamical system 1. And now I'll give you the theorem for So Peixotto's theorem in 1D. And you can read this, so on the PDF notes, I gave you a link to my paper that has this proof that I did with Professor Blackmore. So you can read up in detail about this proof, but today I'll kind of outline everything. So this is our theorem. So it says suppose 1 is a C1 dynamical system on S1, then 1 is C1 structurally stable if and only if, so we have two parts to this proof. We have the if part and the only if part. If and only if it has finitely many fixed points all of which are hyperbolic. So the first part of the proof is going to be easier, but more tedious. And the second part is a bit more difficult to kind of think of, but it'll be more interesting in my opinion. So let's do the first part of the proof, but let's do a special case first. So proof, and then we're going to go, so this means that we are assuming that, so we're going to assume, so we want to go backwards actually. So we want to say that it has finitely many fixed points. So we actually want to go this way. So we want to assume that our system has finitely many hyperbolic fixed points. And then we're going to show that it's structurally stable. So if we have finitely many hyperbolic fixed points, then what is one case that we can think of? What is one trivial system that has finitely many hyperbolic fixed points?
X?
Hmm?
X?
It's not quite trivial though. Let's think of just a trivial system. So how many fixed points, let's say? So finitely many. So just 0 fixed points, right? So that's a system that has finitely many hyperbolic fixed points. So it has 0, right? So it has no fixed points. So let's do that case first. Case 1, no fixed points. Now let's see what this looks like. So let me draw these here. So this is f of x. This is x. That's 1 over there. It's 0 over here. And this is going to look something like this. And I have to make sure that the derivative is going to be equal, so it's going to be something like that. So let's say we had something like that. No fixed points whatsoever. Well, let's take a ball around it. And obviously, I won't be able to take care of the derivative. So we're just going to have to pretend that the derivative is taken care of. But let's take a little ball around it, and let's pretend that we are also considering the derivative. Obviously, I can't sketch that, but let's just use our imagination to think of, to pretend that we're taking care of the derivative. So we can see that if we're changing this, right, in this little ball, we're still going to have 0 fixed points, right? So what does it mean for the dynamics to be the same? Let's think of that. So if we add fixed points, obviously the dynamics will change. If we take away fixed points, the dynamics will change, right? So here, in our original system F, we have that the flow is just to the right, right? So that's what the flow is. So it's just going to be to the right, and it's going to come back on itself, right? So the flow is just to the right, it's just going around in circles. Well, if we take any system inside this ball, we get the same sort of thing, right? We get that the flow is still to the right. So the dynamics are the same. So that's the idea pictorially, but let's write it down. And since I don't want to go take too much time, let me just tell you very quickly what it is. So that's the idea pictorial. So no fixed points means that F is going to be greater than 0. So we agree with this. So without loss of generality, let's assume that F is actually greater than 0. So instead of just the absolute value of F, let's take F to be greater than 0. So that's without loss of generality. Now, F is continuously differentiable, which means that there exists an epsilon greater than 0 such that F is greater than epsilon naught for all x in 0, 1. Right? So that means that since this is continuously differentiable, then there's going to be some epsilon that it's greater than, right? So here we can choose some epsilon naught that this thing is going to be greater than, right? So that's the idea. So we have that, and now consider, so now we're going to consider our other dynamical system. So consider y dot equals g of y, which is also continuously differentiable on S1. If, so now we're saying that if we're close enough, right? So that's the idea. So we want to be close enough. So if g minus f is less than epsilon, which can be less than epsilon naught. So we're going to choose epsilon to be less than epsilon naught. So if we have this, then g is also greater than 0 on S1, right? So we can see this here. Any g in this ball will also be greater than 0. So g is also greater than 0 on S1. So we can choose epsilon to be less than epsilon naught, and so what did I have before that? Oh, okay, and we can choose h of x to equal x. So we could just use the identity map, right? So all the orbits here are going to map exactly to the orbits of g, if g is within this little ball, because they behave the same. So that's the idea. So we can use the identity map. So the identity map is a topological equivalence. So that's for no fixed points. Now let's think of something for finitely many hyperbolic fixed points. So we want to take this picture again. This sort of picture. So I want to draw it like this now. So let's have f of x x here. Let's say we start like this and it's doing something. But these are all hyperbolic. So this is 1. That's 0. So this is x and f of x, and let's do the same type of thing. So let's pretend that we're careful with the derivatives, but we're not being careful. But let's just pretend we are. Okay, so let's say we're in this little ball. Okay? So now we see that if we're in this little ball and we're careful about the derivatives. Of course, if the derivative changes, we can add fixed points and stuff like that inside this little region. But we don't want to do that. So we want to be careful about the derivative, but let's pretend we are being careful about the derivative. Then we see that any sort of dynamical system within this region will have the same number of fixed points, and the stability of the fixed points will be the same. So that's what it means for the dynamics to be the same, right? So same number of fixed points, stability is the same. So that's what that means. So this is case 2. So this is the real proof of that portion. So this is case 2, and then once we're done with this, we can get to the fun stuff. So let's assume that it's finitely many hyperbolic fixed points. So we're assuming it's finitely many hyperbolic fixed points. So this means that f of xk is going to equal 0, where f prime of xk do not equal 0. So xk are the fixed points. So xk would be like over here. So like this would be an xk. So xk are the fixed points. So we have that they're fixed points and they don't equal 0 for k equals 1 to m. And without loss of generality, let's assume xk aren't endpoints. So without loss of generality, assume xk are not endpoints. And we can assume this because if it is an endpoint, then we can just translate it, right? So we could just translate it away from the endpoint if it is an endpoint. So let's just go ahead and assume it's not, since we can just do a very easy translation for that. So let's assume that it's not an endpoint, and we have to order it, right? So it has to be orientable. So we have to order it as such. xk is less than xk plus 1 for k equals 1 to m minus 1, and xm is less than x1. So that means we're basically going to go around in a circle. So that's what that means. And choose, so again we're going to choose this epsilon naught and delta greater than 0. So epsilon naught and delta are greater than 0, such that the derivative of f of x is going to be greater than or equal to 2 epsilon naught. Why 2 epsilon naught? Well, it comes out in the calculations. So this is the case on each interval. So this is the case on xk minus delta to xk plus delta. So we're basically putting a ball around these xk's. So this is the interval that we're talking about. So we're putting some sort of ball around this interval. So this part is going to be xk minus delta, that's xk plus delta. So we're just isolating these fixed points, basically. So we want to be isolating these fixed points So this basically means that f is monotonic with a single zero on each of these little intervals. So we're just going to isolate these fixed points, and we're going to define, so define k, not, maybe I should call it kappa. Define kappa of delta to be, so here it's where it gets a little difficult, to be the closure of the complement of the union of the intervals. So basically, I want this kappa of delta to be all the points that aren't in these intervals except for the endpoints. I want to include the endpoints of those intervals. But other than that, it's excluding every single point. So that's what that means. So I want kappa to be everything that aren't these intervals. So all the points that aren't in these intervals. So that's how I want to define kappa. So kappa's that. So then f does not equal 0 on k, on kappa. Right? So if I want kappa to be all the points that aren't these intervals, then clearly f of x is not going to be a fixed point. So we're not going to have a fixed point on kappa. So f is going to be not equal to 0 on kappa. So that's basically what it's saying. So kappa is everywhere that's away from the fixed points. So that's the idea. So this is the case on kappa. Now we're going to use continuously differentiable again. So since f is continuously differentiable, this implies that there exists an epsilon 1 between 0 and our original epsilon, such that f of x is greater than or equal to 2 epsilon. 2 epsilon 1 for all x in kappa. So that's how we're going to set this up. So this is the case, then choose. So here we're going to choose our epsilon to be the minimum of epsilon 1 and epsilon naught. So it's the same sort of idea. So we have to do all this setup in order to choose our epsilon. So here we could choose our epsilon very easily. Obviously here it's a bit more difficult to choose it. So here we're going to choose our epsilon to be the minimum of those two. So then this means that G has a single 0, yk on each of these intervals, on each interval. So that means our y dot equals g of y is going to only have a single 0 on each of these intervals. So basically what we showed there is that for our y dot equals g of y, we're not changing the number of fixed points. The number of fixed points are going to be the same. Now we want to worry about the stability. So we have yk and none on k. So on each of these intervals and none on k, on kappa. So we're basically saying that the fixed points aren't the number of fixed points aren't changing. And none on k, and the same sign as f on this, and the same sign. Okay, so and same sign on intervals. So it's going to be, we're saying that G is going to have the same sign as F so on G is going to have the same sign on yk minus delta to yk plus delta as f does on xk minus delta to xk plus delta. So that's the idea of that. So it's going to have the same, or sorry, yk and yk plus 1 as x does on xk plus 1, as f does. So that's the idea for that. And now we can choose our homeomorphism. So here we actually have to find a very difficult, quite a difficult homeomorphism. So here, and this is the end of the proof, of this portion of the proof. The next portion will take like 5 minutes. So this is h of x is going to be y1 over over x1 x on 0 to x1, and it's going to be yk plus 1 minus yk x plus yk xk plus 1 minus xk yk plus 1 all over xk plus 1 minus xk for xk for x between xk and xk plus 1. And the last portion is going to be, so let's see. Oh, right, so this is for k between 1 and m minus 1, and then the last portion is ym over xm minus 1 times x minus 1 for x between xm and 1. So that's our homeomorphism. So this matches up fixed points, endpoints, and the orientation. So that's our homeomorphism. And then really quickly, I'll do the last portion of this proof. So this will probably be the longest proof we'll see in this course. So here's the last portion. So this is going the other way, actually. So now, so we can either, so we're assuming that it is structurally stable, and we want to show that it has to have finitely many fixed points, all of which are hyperbolic. So what we can do is use the converse. So that means that if it has more than, so if it has infinitely many fixed points or non-hyperbolic fixed points, then it can't be structurally stable. So that's what we want to prove. So we want to show that if it has infinitely many fixed points or it has non-hyperbolic fixed points, it's not going to be structurally stable. So I'm going to draw pictures for these. So for the first case, so we want to remove or add fixed points or change the stability. So for the first case, let's think of this. Let's think of a fixed point that goes like this. So it's tangent at one point. Now, do we want to remove or add fixed points there, do we think? Well, it's probably easier to, okay, yeah, we can add. We can also remove the fixed point as well. So let's think of removing it so we can do everything in the positive domain.
Okay.
So if we have a case like this, and we want to remove that fixed point, how can we do that?
Add a constant.
Okay, we can add a constant, so that's a very good idea. But if we add a constant, there might be a fixed point down the line, right? So that fixed point might be translated to a different fixed point down the line. So we might have something where, so this does something, it does something, and it might have something where it goes like this. So we add a constant, this comes up and becomes that fixed point again. So it's the same fixed point, right? By adding a constant. We're going to use something called a bump function. So for this, we're going to use a function where between -1 and 1, it looks like this. It looks like a Gaussian. And then after -1 and 1, it's just 0. So that's the type of function we're going to use. Now what we're going to do is we're going to close this in on the fixed point, and we're going to shrink the amplitude of it. So let me just tell you what sort of function we're going to use here. So this function basically looks like this. So this is going to be the exponent of -1 over 1 minus x squared for x in -1 to 1, and 0 for x not in -1 to 1. So that's a bump function. So we're going to use this. So over here, so you know what? I'm not going to write it down. So over here, we're just using a little bump. So basically, we're going to be using this. So we're going to use like a little tiny bump. So something like this, where this is negative x, or x star minus delta, and this is x star plus delta. So we're going to be in this ball of radius delta, and we're going to just use this little bump. So what happens is that we can remove this, but we don't affect anything outside of that little region. So if we have a case like this, we can just use these little bumps for each of these cases. So that's the first case to prove that that if we have a hyperbolic fixed point, so here we have one hyperbolic fixed point. So if we have a hyperbolic fixed point of that kind, then we can remove it just by using a bump function. So the second case is going to be this. So let's say we have something like this. So this is tangent over here, but it's tangent that way. So we can't just use a bump function to remove that. So let's use, say, 2 bump functions to add a fixed point. Or we're going to add 2 fixed points. So what we're going to do is pull this one down. So let's introduce a bump function like this. So we're going to pull that down, and then we're going to pull this one up. So we're going to introduce a bump function like that. So that will add 2 fixed points. So basically what we get out of that is going to be this. So it's going to look like this. So it's going to look like that. So we're pulling this one down, and we're pushing that one up. So that's the idea for that case. So we could just remove it in that manner. And now let's think of one final case, and then we're going to stop. So this is case 3, and let's think of a line of fixed points. So let's say we have something like this. So let's say we have an entire line of fixed points. Well, for that, we can use an extended bump function. So here we have the bump function, and then let's just extend this. So in that way, we basically remove this line of fixed points, and it becomes this. So I probably shouldn't draw it like that. I should draw it like this. It becomes, it does whatever before, but it goes into this. And continues doing whatever it does. So we can remove fixed points in this sort of manner to show that if there are infinitely many fixed points, or there are non-hyperbolic fixed points, then it's clearly not going to be structurally stable, right? So we remove a fixed point, well, we change the number of fixed points. So it's not going to be structurally stable. If we add fixed points, we change the number of fixed points. Not going to be structurally stable. If we remove infinitely many, we change the number of fixed points. So it's not going to be structurally stable. So that's the idea. So there's one more interesting case in the paper I wrote, but we won't do that in this class because you need some analysis to really understand that. But that's, once you learn some analysis, you should kind of look at that case. So yeah, that was structural stability and Peixoto and Poincaré maps. So any questions before we head out?
I thought that we couldn't change how many fixed points it has. I remember you saying earlier, like, well, this right here is for this proof that you know, right?
Wait, what?
Earlier, I remember you were saying like put a ball on a function or something like that.
Oh yeah, so that was for the case where we have finitely many fixed points. We have finitely many hyperbolic fixed points, and we're going this way into the proof.
Okay.
Right, so we're going from here, and we're going to show it's structurally stable. But we have an if and only if over here, right?
Okay.
So we have to show that, so it's structurally stable only if we have this, but if it's structurally stable, then we have this. But now what we can do is just use the converse. So in order to go this way, we're saying that if something is structurally stable, then it has finitely many hyperbolic fixed points, right? But that's difficult to show, so let's use the converse. So the converse says that if it has infinitely many fixed points, or it has non-hyperbolic fixed points, then it's not structurally stable. So that's the converse. If you can prove the converse, then you've proved it. So that's the idea. So yeah, that's the biggest proof we're going to do in this class. So I guess you can show your friends the notes you took on this. Yeah, you should look at my paper. I told you guys about the proof, right, in Calc 2?
Yeah, you mentioned it.
It's like 14 pages.